Now that we have the harvesting function, we can use it to describe the dynamics of natural resources and the population on Easter Island. This dynamic will be two differential equations describing how our two state variables evolve. The state variables are, of course, nature and islanders. So the first state variable is the resource at time t, which we denote S of t, of course. We label G of S of t the logistic growth of the stock of nature. So it has the familiar form G of St equals to R St, which multiplies 1 minus S of t over K, where of course K is the carrying capacity, it's the maximum amount of resources in the long term if resources grow and if there is absolutely no extraction, no exploitation of a resource. And R is again the regeneration rate, which is between 0 and 2 if we want to have a nice solution. Now the law of motion of the resource stock is written S dot of t, which is simply the derivative of st with respect to time. So we write it S dot of t simply equals to the natural growth rate, and the natural growth G of st minus the harvest at time t H of t. We now substitute both functions, so let's write it again as S dot of t equals to simply R S of t, which multiplies 1 minus S of t divided by k, minus the harvest, which is, as we have found, alpha, beta, S of t, L of t. So now what we have just done is introduce L of t to describe the dynamic of the stock. Why? Because the number of inhabitants on the island will dictate how much harvesting is going on, so it will affect how much the nature can grow. We have both the nature stock and the harvesting that are sort of proportional to ST. So that's because the more nature we have, the fastest it can have descendants or offspring, so the easiest it is to grow. But also, you know that the more ST, the larger it is, then the more exploitation we have because it's easier to harvest if there is more nature. So that means that we can put ST in front of the parenthesis and write it as follows. So S dot of t, the derivative of ST with respect to time, is equal to ST, which multiplies, let's write it, R minus R over K, which multiplies ST, minus alpha, beta, LT. So this equation is important. It's the praise dynamic in the Volca-Volterra model. So it's a differential equation because it links the derivative of ST with the stocks of prey themselves ST and of predator LT. So how do we interpret it? Well, the outside ST is obvious. The more nature, then the faster it reproduces. But inside the parenthesis, two things are going on. So if ST increases, it means that we get closer to carrying capacity. So this limits how how large it can be. And also, if more islanders are around, then they exploit nature more, and thus the stock of nature doesn't increase as fast. Whenever we have a system of differential equations, their dynamics can become quite complex to describe. So the trick is to start dealing with what is simplest. So what is the simplest case? The steady state. So the question is, for what set of values is the system not moving? Well, here the movement is that S dot of t. So at steady state, S dot will be represented by S dot star, and it has to be 0 if the stock of nature is at steady state, so it doesn't change. But note that since we have two state variables, S and L, then both need to be at steady state. So we're going to write S star and L star. So the equation simply becomes S dot star equals S star, which multiplies R minus R over K times S star minus alpha beta L star. And this, of course, at steady state has to equal 0. So how many solutions do we get for this equation? I let you think about it. Well, since this is a product, then it's obvious that we get actually two solutions. So the first one, we'll call it the barren island, which is when S star equals 0. And in that case, note that we don't care about the value of L star. It can have any value. So the interpretation, again, is simple. If there's no nature, then it cannot grow. So no matter how many humans on the island, if the island is empty, then that's it. No, nature doesn't grow. The second one, of course, is the more interesting one. So let's call it the sustained island, which is when we have some stock, but inside the parenthesis is 0. So that means that we have R minus R over K, which multiplies S star minus alpha beta L star, the number of islanders, equals to 0. So let's express S star as function of L star. This will be useful later. So what we can do is just write R over K times S star equals R minus alpha beta L star. And then after dividing by R and multiplying by K on both sides, we simply get this solution for S star, which is equal to K minus K, which multiplies alpha beta divided by R times L star. So we call it the sustained island because there's a positive amount of resource and harvesting is just the same as the natural growth of the stock. So how do we interpret this inverse relation? Think about it. Why is there a minus in front of the term for L star? Well, because if L star is higher, then if there is more islanders on the island that are harvesting, then S star cannot be too close to carrying capacity, otherwise the natural growth would be 0. So it means that the stock S star has to be not too large compared to the carrying capacity. Yeah. So we'll now show what we call a phase diagram to show this dynamic of S graphically, and it will make more sense. This is what we call a phase diagram. It's going to be a representation of the evolution of both stocks as function of their values. So we have on the x-axis L, the number of workers, which is actually the number of islanders on the island, and the stock of nature S. And here we are going to show how, if S and L have certain values, how both of their values are going to evolve over time. Of course, for that we need the dynamic of both stocks. Now we only have the dynamics of the resource stock S, but we start with that and then we add the dynamic of L. So one thing at a time, it's enough. Here I've reproduced the equation. So S dot of t equals to st r minus r over k st minus alpha beta lt. So this describes how S changes. So if S goes up or goes down as function of both S and L at time t, so it can have any value. And to make sense of this, the trick is always the same, is to start with by asking ourselves which are the values for which S is not going to change. So let's start with the first set of values here that we just computed. It's the sustained island steady state. So S star equals to alpha minus to K minus K that multiplies alpha beta over R times L star. So then this describes a set of points on this graph that for which S does not change. So here we don't care about how L changes. We're just going to look at how S changes. All right. So what does this look like? Well, it should look like a straight line because it's a function of affine function of L, and it should have a negative slope. So let's just go ahead and show the function. So it should look like this. So this describes a set of points for which S dot equals to 0, and it is because the interior of this parenthesis here equals 0. All right. And now the question is, so we already know that the slope here is minus K alpha R over alpha beta over R. And then what we can ask ourselves is, what are the intercepts here and here? So to know that, we would have simply to compute them. So to imagine, first of all, if S equal to 0, what is the value of L? And if L equals to 0, what's the value of S? So let's just go ahead and start with L. So imagine that L equals to 0. What is the maximum value of S that makes S dot equals to 0? Well, you just substitute L star with 0 here, and we find that, of course, S star equals to K. So we know that the intercept here is K. And then the other is, of course, if S star equals to 0, then in that case we can divide by K on each side, and we find that S star must be equal to R divided by alpha beta. So let's go ahead and write these two values there. So that's the limit of the dynamic of S in the sustained island case. So is that the only possible solution for a steady state amount of resources? No. We know that it's also possible to have a barren or a barren island with no resource at all if S star equals to 0. So what would that look like? Well, simply it would be all the set of values for which S star equals to 0. And as we said, we don't care in that case if whatever the value of L, that doesn't matter. Of course, it could be infinite, but we can just limit ourselves to these values there, and then indicate them this way. So S star equals to 0. So all of this set of points are all the combination of S star and L star for which S dot T is equal to 0. All right. Now, last thing we have to ask ourselves is, so this is steady state for S, but of course then what we want to know also is how would S change if we were not at steady state. So for instance, imagine that you start with some value here of S and L, and then for some reason the value of S changes, for instance. Imagine that S increases. So we go up, for instance. Then the question is, how will the stock change over time? Then what you have to do is look at your dynamic change equation there. And you know that in that case, it's not S is not 0, so this is not 0. But since S doesn't change, then it means that the parenthesis here is 0. And then you ask yourself, so imagine that you start with S star and L star, and then S goes up. So what happens to S dot? Well, if S dot was 0 and now S goes up, then how is the value of S dot going to change? Well, it will become negative because I have R over K negative here. Same thing if I were to ask, what if L goes up? So if L goes up, then this was equal to 0. So S dot was equal to 0. And now L goes up. So there's a minus alpha beta in front. So it means that S dot will again decrease. So it means that all the set of points that are to the up and to the right of this line are going to describe a point places in which the stock of nature goes down. And then, so I can just indicate this with an arrow. That's how we indicate it. So we know that if we start at steady state and then the stock of nature goes up, then it has a tendency to go back down. The interpretation is that if it goes up, then we're closer to the carrying capacity of the ecosystem, so the tendency is to go back down. And here, if I increase the number of islanders, then they harvest more, so the stock again has to be decreasing. And of course, the opposite would make sense too. So if I start at steady state and for some reason I decrease the number of resources, how is the dynamic of S going to change? Well, this was equal to 0, and now I'm decreasing S. So it means that what's going to happen to S dot? Well, S decreases, there's a minus there, so S dot is going to increase. So on that side, then if S goes down, then it will have a tendency to go back up again. Same thing if L goes down, it means that I have fewer islanders that harvest, so it will be good for the stock of the resource, so S dot will be positive. So I can indicate this with an arrow there. So this describes the whole dynamic of the stock of resources. That's just one of the equations. We're now going to do the same for L, but so to not get too confused, you have to do it for one and then really know what's going on, and then you can do it for the other as well. So let's do that now.